Hello, everyone. I'm presenting semi-supervised semantic segmentation work using generative adversarial network, which is a joint work with Dr. Concetto Spagnato and Dr. Virayak Shah. So as you may know, semantic segmentation is assigning a label to each pixel of the image. For example, given these images and a set of classes like categories, like building, cars, etc., we want to come up with a segmented image that it has pixels and labels for each pixel as well. And this is a challenging task because we have to segment as well as recognize the regions in the image. So there are many models and approaches for this problem, but most of them, they are supervised approaches, and they need lots of annotated data. And as you know, the annotation here is pixel-wise, and it's very hard to obtain. So on the other hand, we have lots of unlabeled data, and we want to use a generative model to improve our model. So for example, if we have this labeled data, our typical and the standard model is using, for example, in deep learning, we use layers, and we have this supervised loss. Then, in addition to that, we want to use unlabeled data and also generative data. And in a semi-supervised fashion, we want to improve our results. An alternative to supervised learning is unsupervised learning. However, unsupervised learnings have not been very successful in semantic segmentation because of the lack of notions from classes. They just try to keep the constant and they keep the regions. But semi-supervised learning is a halfway between supervised and unsupervised learning, and we want to use that. We want to use smoothness constraint in semi-supervised learning. The assumption here is if we have data points that they lie on the same feature manifolds, we want they be close in the next space. For example, in our case, is a segmented map space. So we want to find the structure of the data. So we use unlabeled data to find that structure. So if this is our loss for semi-supervised learning, this part is for when we have the labeled data. These Y's are labels, and we add the loss for unlabeled data. And this is like a generalization of our model because this plays like a regularization for our model. So generative adversarial network are very successful generative models, and they provide unsupervised learning. This is an example that shows the intuition behind the generative adversarial network or GAN. We can assume that we have a painter that he wants to do art forgery. We call this G. And also we have a judge that his role is to judge the painting, see if this is real or fake. We call that D. So G paints these paintings, for example, Picasso paintings, and he wants to fool D, the judge. On the other hand, D starts learning more about this real data and the real paintings and like fake paintings. And so G has a harder time to fool D. And so along the way, these two, D and G, both of them get better in their job. So D gets really good in telling apart what is real painting and what is not, and G at the end learns to paint more realistic paintings. So in terms of image generation or generating the images, this is an example from ImageNet datasets. So starting from a noise generator, which typically it's a network with the convolution layers, transform this noise to a synthetic image. And then we have training data. These are real data from our training data. We call that X. So discriminator, which in a standard GAN is just binary classifier, learns to distinguish between the generated data and the real data. And this is the generated images for ImageNet. For example, you can see some classes like dogs and other classes in this generated images. So for the optimization, as I said, GAN consists of two networks, a generator G and a discriminator D. G starts from noise and transforms that noise to GZ. G of Z is a synthetic data or synthetic image. And D, the discriminator, takes these images from real data, or real distribution, and also from G, the fake data, and classifies them as a D of X and D of GZ. So these two play a min-max game between one another. And in this case, discriminator discriminator should optimize in a way that increases likelihood of giving a high probability to a real data and low probability to a generated data. On the other hand, the generator is optimized to increase the probability of generated data being real. So how we use GAN in semi-supervised learning? So in our case, labels are not available for all training data. We want to use unlabeled data to estimate a proper prior to improve our classifier and make our classifier learns better features or robust features. So our GAN model uses unlabeled data, and it tries to increase the probability of unlabeled data belong to the same distribution of the labeled data, and the generated data should not belong to this distribution. So the idea is applying the same filters from network to images from the data distribution. The unlabeled data lead to similar categories, similar classes, while the output of this different data or the generated data should be far from the labeled data. So this is our architecture of our model. So the first is I should say that the discriminator here is different from the standard GAN. Our discriminator is semantic segmentation network. It's a fully convolutional network, so it gives us these maps. Each map is a probability map for each class. For example, if we have K classes in our training set, we add another class, K plus 1 is a fake class. So the standard way to do semantic segmentation using fully convolutional network is use the label data and go through this network and get those probability maps. But we add unlabeled data as well as fake data that is generated by a generator. So for optimization, discriminator classifier is, as I said, is semantic segmentation network. So we use VGG network with the convolution layer. It's a standard fully convolutional neural network for semantic segmentation, and you can replace this with any other semantic segmentation network. And for a generator, the generator starts with the noise. The noise is a vector of dimension of 100 that's sampled from uniform distribution, and followed by different deconvolution layer. At the end, we get RGB images. So first we have the noise, then we use a linear layer to increase the dimension of that, and then we followed by some deconvolution layer. At the end, we get this synthetic RGB image. So the optimization, the discriminator loss consists of 3 losses. One is for unlabeled data, one is for the fake data, and one is the typical supervised loss. So the first part is We want to, for this part, the P data is for unlabeled data. We want to increase the probability of the output of discriminator for a real image belong to the real data. And this part is for, we enforce the discriminator to label fake data as a fake, or generated data as a fake. And this part is the typical cross entropy for the label data. And the gamma is just the way that we can have to put more emphasis on label data or not. So dx is output of discriminator, and it's just probability of being fake or not. And we find the probability using softmax. So for the generator should be optimized in order to minimize being fake. Or so this is, or equivalently, we can just maximize that this is real. So the optimization and the alternative gradients between the two networks. Now, when we get a new data, or when we have the training data, after each batch, this generator slowly converge to produce more realistic data, and the data that they have classes that we have in our training set. Now we extend our model to use weakly labeled data as well. If we have weakly labeled data, and by weakly labeled here I mean image level labeled data. So the generator, for generator we use conditional GANS. So the generator uses noise as well as class label information. And discriminator also use the generator data, same as the semi-supervised way, and unlabeled data, image level labels, and again the fully labeled data. So we modify our architecture. For the generator, we add class information, and for the unlabeled loss, we have the image labels. So as I said, we use conditional GAN when we have the class information, and in discriminator, we change the loss. Now, the unlabeled loss should maximize the probability of being of seeing only those labels that we have in a training data and we have in a ground truth. So this is the conditional GAN formulation. It's very similar to typical GAN. The only difference is now we have L. L, it's extra information that we condition generator on the L. And this is the modification of the loss of discriminator. So when we have KIs, KIs are the image level labels that we have in a ground truth, we now want to maximize the probability of those classes. And still we have to label the generated images as fake. So we tested our method on different data sets for different data set, Pascal Work 2012, SiftFlow, Stanford background, and Cambit. And we have 3 different metrics: pixel accuracy, per pixel classification accuracy, and average of region intersection over union, or mean IU. So for the first experiment, we use Stanford background data set. We compare with this method that they also use somehow GAN to generate the segmented image, but our model is different from theirs because we have our discriminator has more layers, and it's more complex model to learn the difficulty of semantic segmentation tasks. So as you can see, we can improve our results, and we get better results using our model. And the other data set that it's a very good fit for our method is Cambit, because Cambit is a long video, but only 700 frames of that is annotated. So we compare with the SegNet and we can get better results, in particular for mean accuracy per class here. Because some classes that other methods, for example, like poll in the street view images, they can't label that correctly, we can capture those classes as well. These are some qualitative results on Stanford background. For example, just using fully supervised, the foreground object is not labeled correctly, but in our case, we can smooth and we can get rid of the false positive. These are more results on Stanford background. Again, we can capture the foreground object correctly. We repeated our experiments on Pascal Work 2012 data set, and for this data set, in addition to unlabeled data, we have this image labels. So if we just use fully supervised, we get 62%. Using semi-supervised, we get 64% mean IUA. And using this weekly labeled data, we can improve further. The other experiments that we have done is if we just use only 30% of fully labeled data, that it's about only 400 images that they are fully labeled. So using fully supervised method, we get 38, and using semi-supervised and weekly supervised, we can get better results, and the gap is higher when you have fewer fully labeled data. These are some qualitative results for Pascal data set. In this case, we have used only 30% of data, like fully labeled data, and you can see semi-supervised method and weekly supervised method improve the results noticeably. Especially, we can get rid of like false positives, again, here for other data, and weekly supervised or using weekly labeled data can help to get rid of those false positives. SiftFlow data set has more classes. It has 33 categories, and we don't have any unlabeled data for SiftFlow, but we use Sun 2012 data set that they have very similar categories and they have very similar images, and we use that for our unlabeled data. So using only fully labeled data, again, we get, for example, for mean IU 25%. Using this free unlabeled data, we get 28. These are some qualitative results for SiftFlow data set. Again, we improve the results. And for example, here, using fully labeled data, at the bottom you can't get the person, but in our method we can find the person. So because of that, the mean accuracy per class gets higher results. These are some generated data that at the end the generator generates this data. For example, in this, the first row is from SiftFlow data set. We have like beach, so we can get sky, sea, or forest. The second row is from Pascal. This is the weekly supervised that it's conditioned on classes. For example, you get dog or plant. And the third one is from Canvas, that it's mostly London and it's gray and it's just street view, and you can get some classes like car. So in summary, we present a novel semi-supervised model for semantic segmentation problem using GAN. We extended model to use conditional GAN and image level label data in a weekly supervised manner. And also, our model generates meaningful synthetic images. Thank you.